All right, thank you. And just let me know if you can't hear me, as this thing might slide a bit. But first, of course, I want to thank the organizing committee for inviting me and also for letting me still consider myself a local speaker, even though I left. So thanks for that. And why don't we jump right in? So a major question driving a lot of exoplanet research today is how do planets evolve over their lifetimes? By which I mean, how do they change from right after they form from a protoplanetary disk to the more mature, evolved systems we see, for example, in the solar system today? And you can think about this question in terms of a number of related science questions. For example, how do planets migrate? How do they change in terms of their semi-major axis, or their orbital period? How do planets change dynamically? Things like their alignment with their host star, their eccentricity and inclination. How do their atmospheres change, both in terms of the composition of the atmosphere and something more measurable like the scale height or how thick the atmosphere is? And how do their structures change? Something like composition, what are they actually made of, and something more easily measured like density. Now, this isn't an exhaustive list, but this is sort of representative of the kinds of questions we're asking when we talk about how do planets evolve over their lifetimes. And more importantly than just how do they change is sort of what are the physical drivers of these change? What is the physics behind each of these evolutionary pathways for any given planet or a group of planets? And this might be things like how the planet interacts with its star. Is it losing atmosphere through interactions with its star? How planets interact with other planets in the system, dynamically and also through collisions. How they interact with their greater environment, clusters, binarity, and then, of course, how they interact with their disk. And again, this is not an exhaustive list, just representative of the kinds of interactions we're interested in, the kind of physics driving these. And I want to work through an example to sort of highlight both the kinds of questions we're asking, why we're asking them, and then how we actually go about trying to answer these questions about how planets evolve. So one of the major findings in the last few years, and more extended over the last 10 years, but most especially since the Kepler results have come out, is that there's an abundance of close-in planets. If you look around M-dwarfs, something like 50% of M-dwarfs have a planet with orbital periods less than 10 days. And if we just consider orbits out to the period of Mercury, then basically 100% of M-dwarfs have a planet, roughly. And it's, of course, significantly lower for sun-like stars. It's something maybe more like 30% or 40% of sun-like stars have a planet within Mercury's orbit. But this is still a very high number, considering we don't have any such planet in our own solar system. And this is especially important because it's very hard to explain the formation of such objects. If we look at protoplanetary disks, and you sort of zoom into this region where these planets would form, it's very difficult to form any planets at all there. For starters, there's not much material, not much planet building material, but more importantly, the dust that we use to build these small millimeter grains that eventually form planets, it actually sublimates at the temperatures this close to the star. So it's very hard to explain how you get a planet this close in. And a similar way to look at this is sort of this exoplanet census figure. This is a common way to look at sort of the state of exoplanets at a given time. This was last updated in 2016, but it hasn't changed very much in that time. And immediately when you look at this, you should see a number of important structures. First is this large gap of planets out at long orbital periods and small radii, or small masses and long semi-major axes. This is just detection bias. These are the hardest systems to detect. Our most prominent methods for detecting exoplanets are less sensitive to smaller planets on wider orbits. That's not quite true of all methods, but most methods have this problem. So this is just detection bias. The bigger question is what's actually going on here. These are the planets that are hard to form, and yet there's clearly tons of them. They're quite abundant. And so the question we want to know here is this some close-in tail of planet formation? Are the planets actually forming this close in? And we have some sort of arc of planet formation efficiency. Like there's some region where planets form best, something like the snow line out at a few AU. And this is why you get this population of very massive, large planets. And then you're seeing sort of the tail here at close-in orbital periods. And that's why maybe these planets are smaller. There are, of course, major problems here. The first one is which, how do you explain these large objects that are very close in? And so a more popular explanation for sort of this, what's going on the left-hand side of this diagram, is a combination of inward migration and photoevaporation. So planets form, again, further out where there's more material and the material doesn't sublimate, and then they migrate inward. And then you explain this gap right here through photoevaporation. So the larger planets can retain their gas disks, so they stay as gas giants for the most part. But planets that are right here lose their gas disks and they become smaller radii. But this sort of just pushes the question to the next step. Assuming this is the correct explanation, then what is the actual mechanism driving this migration? And speaking very broadly, we can break different planetary migration mechanisms into a few different classes. One I'll call disk migration. This is interactions between the planet and the disk from which it formed. And there's a bunch of different types of disk migration, but for the purposes of this discussion, we're just going to lump them all into one. And then this other class we'll call three-body migration, which is interactions between the planet and another massive object in the system. And it's basically just angular momentum exchange. In the case the other massive object in the system is a star or a very massive planet, we call this Kozai-Leadov. And in the case it's other planets on tight orbits, for example, at resonance, we call this planet-planet scattering. And this isn't exhaustive. These are sort of the most popular migration mechanisms. And like I said, there's different types of disk migration. And in fact, there's different types of Kozai-Leadov and planet-planet scattering. So this is a very broad breach of the different migration mechanisms. But this mostly covers the most popular methods. So now we have a very typical hypothesis testing type question. We have different models for how planets could migrate inwards. And then, of course, we want to compare that to if they formed in situ. And so we need to actually test which one of these is right. And this is sort of a classic planetary evolution type question. And the typical approach to this problem is to take some population of the planets. The population could be all of the known planets if you want, or you could pick some subset. You could pick, for example, these large close-in planets, the hot Jupiters we call them. And then you select some parameter of interest. And in this case, I'm going to pick eccentricity and orbital period, but you could pick anything that's observable. Planet-star alignment, you could pick the semi-major axis distribution, the multiplicity of systems. And then you run a number of simulations. And so you make a bunch of assumptions about how these migration mechanisms work. And then you come up with a distribution in this parameter. So using these two examples, eccentricity, disk migration tends to dampen eccentricities, whereas Kozai tends to ramp them up. And disk migration tends to drop planets at discrete orbital periods, which is basically where the disk is truncated, whereas Kozai tends to throw them all over the place. This is very rough and qualitative. But then once you've run these sort of simulations, you then compare them with the observations. Very typical hypothesis testing. And there's probably more than 100 papers that have done this exact sort of thing to answer these exact kinds of questions about planetary migration. But you can already start to see the problem. Different parameters that you use produce different results. And more importantly, how you run these simulations makes a big difference. So there are literally people who are working with the same parameter and similar sets of planet populations. And so two different groups looking at the eccentricity distribution for a similar but not identical set of planets are trying to reproduce these observations with their simulations, and they're coming up with different results about what the most likely migration mechanism is. And of course, some of them can get away with using mixed modes, like it's partially disk migration, partially Kozai, and you can sort of fudge a little in there, but the basic point is the same, that different groups are getting different answers this way. And part of the problem here is that these simulations have a huge number of free parameters, and they're highly chaotic, they're nonlinear. And for any simulation you run, you have to make sort of a key set of assumptions having to do with what the system looked like when it was very young. You have to make assumptions about the disk or the planets, about the host star, about the greater environment, and about the physics that you include. Basically, you can't include all the known physics in these simulations, or they would run only slightly faster than real time. And for all of these assumptions, there's some subset of assumptions underneath them. And each of those has some subset underneath them. And this explodes very quickly. And different groups treat these differently. And so as a result, you can get basically the answer that you want out of this. Now, I'm not trying to besmirch simulations. There's tons of interesting things you can learn about early planetary systems with simulations. But it's more a greater point about being cautious about where you can use these and where you can't, and what parameters you really know and what you don't. And a good example might be this question of environment. So this is something where you might think you know the answer, but you actually don't. So you might think, well, I know if this planet is in a binary, or sorry, if the star is in a binary system, and because I can go and detect it. And if I don't see another star there, then I know it's not in a binary. And this seems entirely relevant for something like Kozai migration, except for the fact that you only know if it's a binary right now. It could have been, it could be single star now and been a binary in the past. Lots of binaries break apart. It was probably a member of a high mass cluster in the past, and it might not be now. And so you really don't know what the environment is when the planet was actually migrating inward, assuming that it did at all. And so you might make assumptions about what you know that aren't actually correct. And that's actually where these parameters are most dangerous, assumptions that you think you know that you actually don't. And part of this is just this bigger point that the exoplanet census itself is just a snapshot in time. We're only seeing these planets as they are today. And yet this method is very widely used to study all sorts of different evolutionary questions, this sort of backtracking, taking an old planetary system and running a set of simulations to figure out what it looked like in the past, or more likely a distribution of planets, not an individual planet necessarily. And this is, for all of these different types of methods. But what we really want is we really want to observe these systems when they're young, when this migration is ongoing, or anything else is ongoing, when the structure is changing, when the dynamics are changing. And more importantly than just observing these processes as they're happening is setting better constraints on the early environment in which these planets live so that the simulations essentially can become more reliable, where we can make fewer assumptions or at least make our assumptions more grounded in reality. So we want to actually see this. And when we ask sort of the next question is sort of how young do you have to go? Most of these different mechanisms, and again, this isn't a complete list, but this is sort of representative. Almost all of these mechanisms are most active in the first 100 million years and maybe gigayear. There's exceptions. There's lots of scenarios you can come up with. Planets are interacting past a gigayear. You can find examples of these. But for the most part, this stuff is happening within the first gigayear. So that's the period we really want to look at. And so if you actually want to observe these interactions happening, you sort of have two options. The first is to find some planet right after it's formed, and then just to sort of stare at it for 500 million years, to catch all the timescales of interest. There's an obvious problem with this, which is the lifetime of most astronomers, as career astronomers, is only about 50 years, order of magnitude. And so this is really not going to cut it, and good luck it's hard to convince NASA and NSF to fund things past 3 years. Good luck getting them to fund something for 500 million years. I would be really impressed. So the better solution is basically what we do in a lot of astronomy, which is to put these on an age diagram. So if you're asking this question, you're picking some parameter you're interested in. Maybe it's how thick the atmosphere is, or the density of the exoplanets. And this would be statistical, not an individual system. And then you're putting it on age on the x-axis, and you're asking how this changes with time. And so let's pick just one example of exoplanet density. And again, this is an average. It's not individual systems. Let's say you saw something like this for some particular subset of planets. This would tell you something about atmospheric mass loss. Are the planets becoming more dense because they're losing radius? Or are their radii contracting because of sort of thermal evolution? Or maybe you'd see something like this, which would tell you the sort of atmospheric mass loss isn't that important, or maybe multiple effects are canceling out. And maybe you'd see something like this, which would be a pretty telltale sign that you didn't do it right. But you can sort of see how this would work. You're basically just putting things on an age diagram as a diagnostic for planetary evolution. The problem, and the reason this hasn't been done until sort of recently, with a few exceptions, is that stellar and hence planetary ages, we assume they're the same, are extremely difficult to determine. There are exceptions. There's techniques. Gyrochronology is one that's become with renewed interest in the last few years. Basically, the way this works is stars spin very quickly when they're young, and they slow down with time as they lose angular momentum through their winds. And so if you can measure the rotation period of a star, you can constrain its age. The problem with this technique, along with many other techniques, astroseismology and isochrone fitting, is that they're subject to large uncertainties. They tend to only work on certain types of stars. M-dwarfs, for example, you can't do astroseismology on them. Gyrochronology doesn't really work. And isochrone fitting gives you biased results because they don't evolve much over their lifetimes. So the majority of stars these techniques don't work on. There are some exceptions. You can get rough ages using, for example, kinematics. But those are also subject to large uncertainties. Also, all of these methods are subject to systematic biases. For example, the presence of a binary companion would bias your measured rotation period. It may also affect the rotation evolution of the system. And if you're interested in something like Kozai, the fact that a binary being there could change your answer would seriously bias your end results. But this isn't even the big problem. The big problem is that planets around young stars are very difficult to find compared to their older counterparts. Young stars have far more spots than their older counterparts. They tend to flare at much higher frequency. And for the very young systems, they probably have disks still present. And all of these make it very difficult to find a planet. And so, when we're taking results from, for example, the Kepler mission, you might think Kepler is very precise. I should be able to find planets around young stars with it. And you could, just a quick reminder before I go into that, Kepler works through the transit method. A planet passes in between our line of sight and its host star. The amount of light we receive from the star drops by a small amount, and this tells us the radius of the planet divided by the radius of the star. So this is basically what Kepler does, and so this is the kind of data Kepler would give you, a light curve. And this is 2 old stars I've picked on purpose because they have planets around them. And you can see this is this kind of data you'd look for a planet in. There is some stellar variability. This is spots on the surface and then spin. And these are old stars. And if you squint very closely, there are planets visible. That's what these little low points are. And then there's some flares visible. It's really not hard to remove this stellar variability to the point where you could find a planet. You can almost see them by eye. But if we take similar mass stars, similar brightness stars that are much younger, the light curves look more like this. You can see that the stellar variability is now an order of magnitude larger. And the flares are more frequent. And there's also structure in the light curve that wasn't present earlier. Basically, what's happening is spots are appearing and disappearing over just a 70-day window. And so you can get low variability and then extremely large variability. And I did not pick these light curves because they're particularly bad. In fact, the opposite. These are some of the best in the young star sample. The reason I picked these is because they have planets around them that we've detected. And by nature, you're more sensitive around the best behaved stars. So these are, in fact, some of your best cases you're working with. And even if you can remove this extremely well, you have to deal with things like differential rotation. So if you phase up the light curve to the rotation period, you'll see small shifts for each subsequent orbit in some spots and not others due to differential rotation. So basically what happens is surveys like Kepler and almost all the surveys before it, with very few exceptions, when you try to plot the planets up on an age diagram like this, you'll find that Kepler gives you a very, very precise answer, but only on the right-hand side of the plot. And this is actually where all the interesting stuff is happening in terms of exoplanet evolution. Which is not to say interesting things aren't happening in old planetary systems. We live in an old planetary system. But this is, if you're interested in exoplanet evolution, this is the region you want, and it is the exact region that Kepler is not sensitive to. Now, there are exceptions, like I said. Different techniques, like direct imaging, for example, is more sensitive to young planets because it's detecting light directly from the planet, and planets are brighter when they're young. So this is an extremely viable technique for detecting very young planets. And basically, prior to a few years ago, was the only technique that had successfully detected very young planets. The problem here is that direct imaging is basically all the points from direct imaging, these are the orange ones, are basically clustered up here. This is where imaging is most sensitive. Now, that's a little unfair. There's a lot you can do out here, and the way I've plotted this in this log-log plot makes this part of parameter space really tiny, but you'll notice actually 2 and a bit planets in our own solar system fit in this period range at least. And so there's a lot of interesting science questions you can answer in this parameter space. It looks smaller than it really is. You can probe, for example, young analogs of our own Jupiter and Saturn. This is a good example, 51 Area B. It's more massive than Jupiter, and it's on an orbit not quite the same as Saturn, but sort of similar. And so we can learn about young analogs of sort of the outer planets of our own system and learn about how they evolve. And this is a very good technique for that. it also has a sort of a bright future. This is where we are right now, but there's new missions, there's new surveys going online. Things like WFIRST is going to push this way further down. You're going to get basically all the gas giants in our own solar system, their young counterparts. And in the very long term, things like LUVOIR and HabEx, one of these will probably get selected, can reach all the way down basically to Earth. And even relatively older Earths. But the point here is that you can do a lot in this region of space where these other methods are insensitive to, essentially. This is the cone where transit and radial velocity and these other methods don't do very well. And we can learn a lot about the young analogs of outer planetary systems this way that we can't do with the techniques that are sensitive here. There's also another method, astrometry. This is essentially, you're seeing perturbations in the centroid motion of the star due to the planet. And this is measured with respect to other nearby stars. The effect is extremely small, so this is hard to see on purpose, because that's how hard it is to measure. And just to highlight how hard this is to do, if you look on the diagram, you won't even see astrometry mentioned here. That's because essentially no planets have been found using this method. That's a little unfair. There's been a few found that are disputed, and there's been a few planets that have been confirmed using astrometry. But essentially the measurement is too difficult to do, especially from the ground, to mitigate other sort of factors that affect your centroid motion of your star. And so basically this is not viable for large populations of exoplanets. That may change very soon with this ESA's Gaia mission. Gaia is an astrometry survey. It's extremely precise. Suddenly we're measuring astrometry in microarc seconds instead of milliarc seconds, thanks to Gaia. And this is an ongoing mission right now and is capable of detecting exoplanets, at least by the final data release. And Gaia should be sensitive to planets sort of in this region. It works better for longer period systems than against more massive systems. And where you put this sort of where Gaia is sensitive plot changes with every Gaia talk I've seen. So I try to do like an average of a bunch of different ones, but when you download all the different talks, I've seen it go way down here and I've seen it further inwards. So I think the reality is they don't know exactly what kind of, what their final precision will be like, but we will probably know that soon and we can get it more accurate. But this is order of magnitude where Gaia will be sensitive. Now the problem with both of these methods, imaging and Gaia, imaging and astrometry, is that they're basically sensitive out here. And again, there's a lot you can do out here. But these are the systems that I was most interested in right now to answering these questions about evolution of planets in the inner system. These are the planets that are really hard to form. And so these are the ones that, for now anyway, I really want to get at these science questions for. And these methods are not sensitive to these inner system planets. So what we really need is we need something like Kepler to look at a large sample of stars with known ages spanning about the age range we're interested in. And we really need a better way to handle stellar variability. So these are sort of the two things we need to solve this sort of problem about the evolution of interplanetary systems. We're very fortunate, actually, that we have both of these. We have the first one in part because Kepler broke. So Kepler, 2 of the reaction wheels failed, and as a result, it was no longer able to maintain pointing. Their engineering solution to this was, instead of pointing at one field of view continuously, they decided to point at a number of fields along the ecliptic. And what this does is this maximizes pressure from the solar wind, basically using the sun as a third reaction wheel. And it doesn't totally eliminate the effect of the spacecraft rolling because 2 of the reaction wheels failed, but it helps mitigate the effect. And this is very fortunate for us because it just so happens that along this ecliptic, there's a number of young star-forming regions and clusters, specifically Praesepe, Hyades, Pleiades, Upper Scorpius, and Taurus. And you couldn't have asked for a better data set to answer these sort of questions about exoplanet evolution. You have very young systems, Taurus and Upper Scorpius. These are the kinds of systems where you're getting planets right after they form, or perhaps even while they're still forming. You have older cluster, older in quotes because they're still young, that should better match sort of the Kepler results at a gigayear and beyond, and you have a data point in between. This is how I would have designed a survey if they let me just toy around with the universe. And you'd end up with almost exactly this kind of distribution. So it's very fortunate. And thus was born this survey, the ZEIT survey, Zodiacal Exoplanets in Time. Zodiacal because it's along the zodiac, the ecliptic, and ZEIT is German for time. And that only took about a week of emails to come up with that acronym. And it was totally worth it, though, because there's actually a number of surveys doing essentially the same thing, looking at these young clusters and star-forming regions to understand how planets evolve, but they don't have fancy acronyms, so they don't get mentioned. The goal, though, is all the same. You want to fill in this diagram using these clusters with the Kepler data point far on the right-hand side of the plot, and then you have clusters at each of these data points in between. And you can do this for any parameter you're interested in, anything you want that you could measure. Now, of course, that only solves one of the two problems I mentioned. We also want to answer this question about how do we remove stellar noise, or at least mitigate it to the point where we can detect planets. So there's a handful of different methods to do this. One is this technique, Gaussian processes. I'm not going to do a primer on Gaussian processes right here, because that's like its own course. I couldn't do a 40-minute talk on that even. But essentially what you can do is use periodic kernels to separate out noise from the instrument, noise from the star itself, and then you can end up with a light curve that is essentially just white noise, well, hopefully just white noise and your planet, right? And so there's the planet right there. It should be very obvious in this final bottom light curve. And so this seems like a very powerful technique, and it is. A number of planets have been found this way, young planets have been found this way. And so it looks very promising. Now in this particular case, you can actually see the, in the raw light curve, you can see the planet by eye, probably. I assume you all can see that. And so this is a good test case to sort of make sure you don't get something crazy. But in the case that the planetary signal is very small, and you're using a periodic kernel, well, transits are periodic. You can actually remove planets this way. And so this technique, while very powerful, can be dangerous. You can basically fit out a planet with a Gaussian process if you're not careful. And part of that is just, you know, the time scales over which stellar variability and planetary transits happen. So this is trickier when the orbital period is tight and the rotation period is extremely tight. And so it depends on sort of this interplay of parameters. So this technique, I think, is viable, but sort of still needs work to avoid this issue of removing real planets. But it has a bright future, I think, for this sort of method. The technique we use is this thing called the notch filter. Essentially what we're doing is you can use a very aggressive algorithm to fit your stellar variability because we include a little notch that it matches the model of a transit. We're taking advantage of the fact that we know that the transit has this trapezoidal shape. And then you can use this extremely strong algorithm to remove stellar variability, because normally you would worry that if you had a very aggressive algorithm, you would remove the transit, or you would bias your stellar variability fit because there's a transit present. And you can see this sort of moving through with various notches to try and avoid removing a transit. Now, of course, it avoids removing noise sometimes. So this is more subject to false positives than some of these other methods, but we have different ways of dealing with that. You can see it move through and it preserved the transits along with a whole bunch of other junk. And this is a good example of when it worked really well. I actually showed this light curve earlier briefly. This is a quite variable star. It was one of the youngest planet known when it was discovered. It's not the youngest anymore, but it's still the youngest transiting planet known. And if you squint really hard, you might see like one of the transits by eye in the raw light curve, but there's no way you would have convinced yourself that that's real based on that light curve alone. Whereas after you run the notch filter through, you get something like this, a very flat, well-behaved light curve, and then the transits are incredibly obvious. You can spot them by eye. You don't even need, a BLS. And this is the final phase-folded light curve, a very clear trapezoidal planet signal, just like we'd expect. And it's not hard to imagine that this detection was quite easy. You can probably detect much, much smaller planets than this. And this is another example of a pretty successful case. The stellar variability on this star is a lot smaller, but the planets are too. So this is a 3-planet system. You can probably spot this one. It's very deep. You can spot it by eye. But I doubt that you can spot this one, which is an Earth-sized planet in the Hyades. So it's sort of a young analog of Earth, except it's not really on Earth's orbit. It's too tight in. But it's hard to find this without sort of more advanced processing techniques. You can find probably these bigger planets more easily, though. But the most important point of doing this, of having sort of our own in-house pipeline, is to measure completeness. So the Kepler survey, they release completeness. They run their own transit search, and they release sort of completeness curves for each of the stars that they measure, that they search for planets around. And so it's easy to understand their non-detections, this issue that we heard about this morning from Samantha. It's just as important here. You want to be able to, you want to know when you're not detecting planets and what you're sensitive to. So you can inject fake planets, and then we can run our own pipeline to see where we're most sensitive. And this is essentially the whole result if you want to do statistics. Because if you're trying to fill out a diagram like this, well, young stars tend to spin faster, and they also have a lot of other contaminating noise. So your sensitivity probably follows some plot like this. It's actually probably more complicated than this, but your sensitivity is a function of time. So you will see trends in your data if you do not correct for your completeness, even if there are no such trends. Basically because you're most sensitive to planets around the older systems. And so this is, like I said, essentially the whole result is hidden in these completeness corrections. But now that we have this, we have the ability to actually answer this question about planetary migration. And again, mostly as an example for how we can do exoplanet evolution more broadly. So in the case of planet evolution, the parameter we're interested in is close-in planet occurrence. The idea being that the planets are still present at some age, but they haven't migrated inward yet. So in the case of disk migration, you'd see something like this. The planets migrate in extremely quickly, and then you detect them all across. In the case of three-body migration, it works slower, and so they move in eventually after like 100 million years to a gigayear, and in situ they're there the whole time. And you notice by design they're all the same after about a gigayear. These are toy models. You can get these curves to move a little bit, factors of a few, by playing around with the model and the details. But fortunately, we're working on a log-log plot, so you really can't get them to change by very much. And here's the actual result, completeness corrected. This is close-in planet occurrence across the different clusters. We don't have a result for Taurus yet. The data only came out like a month ago, but it'll come soon. And these are sort of the different models. So this is an extremely good fit for a three-body migration scenario, and an extremely poor fit for in situ and disk migration. Now, there are planets here. There's at least one in Upper Scorpius that we found, and that suggests that three-body migration is not uniform, but it at least suggests that this is the dominant mechanism. The error bars are quite large. We don't have a lot of planets, which is another point I want to make, something worth taking, I hope, out of this talk, which is that this is only about a dozen planets in this whole sample, whereas Kepler found something like 4,000 planet candidates. And yet we can sort of answer this question, I would argue, better with just these 12 planets than Kepler could with many thousands of planets. Which is not to say that the Kepler sample is useless. It's extremely powerful. There's tons of science questions you can answer with it. But there's sort of this bigger point that it's not always about the most planets. It's about the right planets for answering the question that you're interested in. And in this case, for this specific question, young planets, you can do more with 12 than you could with thousands of old ones. But more broadly, this scenario sort of result favors a scenario of that I mentioned before, inward migration and photoevaporation. Planets form further out, and then they photoevaporate, explaining this hole here. But one of the predictions of this scenario is that if you catch a planet young enough that it just migrated inward, it hasn't photoevaporated yet. So we should see bigger planets around the younger stars than we do around the older stars. And we do. In fact, we see that. In fact, this is one of the early finds from this survey, and basically all the other surveys looking at these young systems. And we have to consider our completeness. Maybe it looks like this. But here are the black points are all these from Kepler. There's probably some young stars mixed in here, but statistically they're very old, a gigayear older, we think. And the young planets that 800 million years and 11 million years are in orange and red. And I hope it's clear that these are statistically offset, at least. And you can ask this question in a more rigorous way. You can say, well, let's say this black distribution is the true intrinsic distribution of planets. What is the probability of finding a planet up here and a planet up here and a planet up there? And you'll find when you add all three together, the odds are zero. This is highly significant. You should have found less than one, essentially, up here. even with our whole survey, especially considering we're not really sensitive to planets down here. So this is highly significant. And we think what we're seeing is this sort of thermal evolution, photoevaporation, and mass loss, so that these are the precursors of planets that land down in the main distribution. And it may be that these two will also drop. We don't know what their final state is. They may end up much lower. And there are ways to test this. We can actually observe atmospheric mass loss by observing the transits in Lyman alpha. And the way this works is if the planet is losing lots of atmosphere, we should see a giant exosphere. And this has been seen before in one specific old planetary system, GJ 436, of which this is an animation trying to describe. And because the exosphere is so large, it makes an extremely deep transit. And it's also got this tail, this cometary tail, so you see an asymmetric transit. And so we did try to observe this in one specific system, this guy right here, K225, mainly because this is the one that is most easily observable. And unfortunately, the result so far looks like we don't see anything. The blue is the model assuming no transit is observed. This is just attenuation, interstellar attenuation, and the orange is the observed data. The point being that we do not see any evidence of an extended transit. So we actually aren't seeing atmospheric mass loss. And then in addition to that, the models of how planets shrink as a function of time predict much smaller changes after 800 million years than what we're actually seeing. They essentially predict very, very small changes. And we're looking at factors of a 2 change is what we need, right? I mean, this thing is about 4 Earth radii, and it needs to be less than 2. And so right now, this can't be the whole picture. We're missing some things. And part of the problem is that we're measuring radii, not densities. So we can only do this sort of statistical offset. And so what we really want to answer is this question of how does the density of planets change with time? And if you look at a diagram like this of radius versus mass, you'll find that for at least the small planets, including the planets in the solar system, they follow a very tight distribution. These are for the older planets. And the hypothesis is that we'll see something like this for the younger planets, but we don't actually know. And the reason we don't know is that the same sort of contaminating signal that affects the discovery of transiting planets that gives us their radii also affects mass determinations. So we can't get masses from radial velocities. And so this is a major impediment to actually determining the densities of these systems. But the situation should change very soon. A number of instruments are coming online or have just come online, specifically SPIRU on CFHT, IRD on Subaru, and HPF here on HET. And these all work in the near infrared, where stellar noise is significantly mitigated. And as a result, you can dig deeper. Stellar activity is much lower, so we may actually be able to measure the masses of these systems this way. In addition to that, we're developing new techniques, and by we I mean the community, not us specifically on this, to deal with stellar activity in radial velocity measurements. And in some cases, this is things like Gaussian processes that I mentioned before, or just more generally simultaneous monitoring with photometry to try and fit for stellar activity simultaneous with a planetary signal. And so the hope is that we can start to get a few data points on this plot to actually figure out what's going on. Why are these planets so big? Since our initial hypothesis seems not to be working perfectly. So there's still problems to be had here. And in just the sort of last minute I have, I do want to talk about this other question, because I think this is what the community is sort of going towards now, both on older and younger planets, which is asking questions about how atmospheres evolve and what atmospheres of planets look like today. And so this is this thing, probing a planet's atmosphere via transmission spectroscopy. And the way this works, imagine you have some planet with a thick atmosphere. At some wavelength, the light will be blocked, and at other wavelengths, it will pass through. And in the case of a transiting planet, when you observe it at different wavelengths, the planet will look bigger or smaller because of this effect. I've grossly exaggerated it here. This is what the data actually looks like. These are different models, but this is sort of realistic uncertainties for different types of atmospheres. And the important parts I want to get out here is near infrared is most useful for model testing, but that the amplitude of the signal is extremely small. But it can be done, most notably from space. Right now with Spitzer and HST are sort of the best tools for doing this, and in limited cases from the ground. But the interesting thing here is that most observations of older planetary systems have found sort of flat-ish atmospheres. So this is the transit depth as a function of wavelength. This is with HST. This is the band where HST is most sensitive to doing this. And you'll find most of these planets are relatively flat. Of course, there's exceptions, but it is interesting that these planetary atmospheres don't show a lot of trends with wavelength. And we'd like to see if this is primordial, if this effect is true for very young systems as well. And so we're following up basically 2 of these young systems very specifically to try and figure out what's going on with those, mainly because they're the most observable. And initially, unfortunately, it looks like these flat atmospheres are primordial. The data is here in black. It seems to match these flat models. Unfortunately, it's based on just one data point right now. Because we only have Spitzer data so far, our plan is to get HST data to sort of fill this in, sort of answer this question more broadly. And I think I'm out of time, so that's a good place to stop. I'll skip the really cool plot of Webb and just leave my takeaways up and take questions.
Great time, Andy. So the plot that has the stellar mass versus the 2 slides back, stellar mass. Sorry. No, okay, yes, on that side. So you have these 2 red stars at the slightly higher stellar masses, and so you said maybe those are going to move down with time. Do you think that's the only explanation, or do you think that there might, like the mass of the star could be a third variable contributing to trends?
Yeah, so the mass of the star is definitely a variable here. And I've sort of picked just the M dwarfs here, in part because that's most of the systems we're probing, but also because it's most obvious here. If you look at the higher mass systems, it does seem that several of our planets fall in a weird parameter space, but it's not so obvious that they're inflated. And so there's probably something like stellar irradiance, which is probably the third variable. That goes into play here. And right now, the sample's a little too small to dig into that. But I actually don't think this is the only variable. This is more just, it looks most stark in this parameter space.
Any other questions? There's one over on just next to you.
Hi, very good talk. So also on this plot, I have a question. I'm sorry, I apologize if you already said this and I just missed it, but so you can definitely say that there aren't smaller planets in these systems, or I mean they're noisier. Right?
So we can't. We can't say that there aren't small planets. We can say, oh yeah, okay, this is what I want. Of course, our detection efficiency depends on the star, but this is sort of a rough forced order approximation. Around the younger stars, we are not sensitive down here. So a more fair plot would just cut off here. We are sensitive to these objects, and we know that from the injection recovery, at least around most stars. And so the lack of very small planets is not significant, but the fact that we find these huge planets is.
Going back to Joanna's question to some extent, go to the primary density plot. Yeah, I mean, you're arguing that the young planets might be in that blue, green, and purple section, and the older planets down below. But of course, you have a whole series of planets who are on the green, blue, and purple lines that are old stars.
Mm-hmm.
So maybe we don't quite understand which way they all go because those should have dropped out.
Yeah. So in fairness, so this particular diagram put together by Courtney Dressing only includes ones with very precise measurements. I think the requirement is 5% or better, or something like that. And a different plot that was not so restrictive would include many points up here. And then even if you make this cut up here, of course, the points are all over the place. And that's sort of expected based on what we understand about planet compression. Well, somewhat expected. And that's, yeah. The limited understanding we have. That's less surprising, was maybe a better comment. But there are points up here. So what is unclear to me is whether the points up here are just poorer measurements. And there are some reasons to think that basically biases in radial velocity when it's a very marginal detection. I don't think that can totally explain this, though. There's too many points up here when you look at the diagram in a different way. But in some sense, that's OK. It makes the measurement harder. We just basically need more telescope time to get a better distribution of planets, because the point being that you would still see a statistical offset. You could still see some distribution. If the distribution is much wider, that's okay. We're still looking for statistical offsets. It's just you have 10 planets. Pleiades and Praesepe have stayed together for at least 800 million years. So in some sense, these are very different regions, but there's sort of this bigger problem that none of them quite match the region where most old stars we're probing probably formed in, high mass clusters that had already broken apart at that point. And that's a bigger problem. I still think we're seeing evolution here and not environmental effects, but environmental effects are still really interesting. And so if it turns out this result is in part an environmental effect, I think that's still really powerful tool that we can use the clusters for. It's less interesting for the specific evolution question, though. That being said, I also think the fact that the planets are bigger, I don't think that's related to environment, because the planets that we have, some of them have already been ejected, essentially. Not quite ejected. They're on the very wide region around a cluster, and some of them are in the core, and we don't see a difference there. Now, that may be those particular, they're not high enough mass, so they don't have B stars in the middle, but we see them in the perimeters and in the middle. So.
So you had Taurus in the K2 field. Do you have any Taurus data? Because you have all the other kind of fields up there in that plot.
Yeah. So the Taurus data only became public in the last month, essentially. And so while we searched for planets in it and haven't found anything, we haven't done the full injection and recovery tests on it. So I can't give you a completeness corrected point on it. I can tell you it's going to be an upper limit because we didn't find anything. And so it's consistent with these. But for all I know, the error bars might be humongous and it might be consistent. Taurus, it's really hard to detect things in. Those stars are really pretty crazy.
As a follow-up to that, how much data would you need, roughly speaking, to distinguish your two evolutionary models to say, to make sure that you are one is truly dominant over the other?
Right. So that's a good question, and I actually I probably have an exact answer to that if you talk to me afterwards, because it was like my test proposal. But the hope is it's actually quite a significant increase, because if you want to separate, let's say between, it sort of depends on the precision you want, but let's say you wanted to say, do 50% of the systems go through this? How much do you need to shrink these error bars? But maybe you're only interested in can I set limits like 20% or 10%? It depends on the limits you want to set, of course, but it's to actually the predicted mixed modes, which let's just say 50-50, it's more than a factor of 2 increase in the total number of targets you survey. But what's going to help even more is surveying brighter stars where you can go deeper, because a lot of our completeness plots are like, oh, we're not sensitive to anything on this star. So that would help a lot if we could just get brighter stars, which TESS gives us. So.
Okay, I think we're going to have to move on to the next speaker. Thanks again, David.